Hi, hello. Thank you so much for coming to this call today and talking with me. If you don't mind, just to start off, could you briefly introduce yourself, as well as sort of explain your both your personal as well as your academic journey to get you where you are today?
Mhm. And thank you so much for inviting me for this discussion or meeting. Myself is Rosna Paul. I'm actually from India. I completed my studies, most of my studies from India. So I have done my bachelor's and master's, and also a Master of Philosophy and MPhil course in mathematics from India. And in 2019, I came to Austria for my doctoral studies. Um, and I joined TU Graz, Technical University of Graz, in Austria, for my PhD studies. And in the past September, I completed it. So now I'm looking forward for new positions and so on. Yeah, that's my background.
Were you always interested in math? Like, was this something you knew you were going to pursue, like as a child or like as a teenager?
Um, from my teenage onwards, I'm interested in maths because I got some happiness after solving some problems. So this happiness is kind of a spark for me to continue my passion towards mathematics. Um, and I also felt I could really think about maths. So for other subjects, sometimes I have to by heart things. In maths, I don't have to by heart a lot of things, but I could get into it with a logical conclusion or something. So that's also very helpful for me to remember things and also follow this logical path. I think that is what made me realized that mathematics is my field. Yeah.
And then I was just wondering, what were some of your favorite parts or classes in mathematics while you were studying in university?
Mm-hmm. From a university, I liked graph theory a lot. My current research was also in graph theory. So this is one field I like the most. Uh, But if I look a whole picture, I mostly follow theoretical mathematics. So it's involving most like real analysis, complex analysis, function analysis, and then algebra, and a lot of theoretical mathematics than the applied level. So my journey was mostly through this theoretical mathematics, but still I felt graph theory is a wonderful subject which connects mathematics and as well as computer science. Um, so I, it's a kind of a bridge course, but still, if you look at my PhD, it's more towards the theoretical part of graph theory. So graph theory is something fascinated me during my studies. Also cryptography, that was also a nice course that I took, but I didn't went a lot of research into it. But still, I felt it's a nice course.
I was just curious, would the existence of quantum computers affect how theoretical graph theory works? Like, is that related?
With the quantum computers,
Yeah.
um, I'm not in a very good position to answer this, but I think if you want to do a lot of calculation, which is kind of a parallel level, maybe the quantum computer use helpful to get the results. But I haven't worked with the quantum computer, so I'm not in a good position to answer this question.
And then I was just also wondering because I think graph theory is very hard from what I know of it. So what's been your favorite parts about like learning graph theory and like doing research related to it?
Mhm. First of all, the introduction to graph theory can be done to a very low, a very small age itself, because it's the introduction to the subject is not that difficult. That is what I felt, because the base of the graph theory is have you have some objects and you have some connections, and how these objects are connected and how do you represent them. So this is very basic idea of graph theory. So what I have done for my research is about graph drawings. So that is also a nice thing to visualize, because you have a graph and you look at how you draw the graph in a plane, for example, and what are the different ways in which you can draw. But while you are drawing, the edges of the graph might cross sometimes. And my main research topic is how to minimize this number of crossings. So how you can redraw it, what all methods you have so that the number of crossings in that drawing is minimized. So even though it's from graph theory, there is a lot of possibility that you can visualize things and to go deeper into what are the different techniques you can use. It's not like you're taking a paper and writing down a lot of equations. It's not like that, because you should imagine, okay, how I can reroute this edge such that it doesn't make much crossings and so on. So I felt it's more a nice thing to do.
And I was just wondering, like, is there a reason why we're interested in like minimizing the crossings? Like, is there an application of that to sort of like the real world outside of theoretical mathematics?
Mhm. So this problem of minimizing crossing was actually originated when there is a mathematician, Hungarian mathematician Turan, who during the Second World War, he has to work in some brick factories where he has to move the wagons containing bricks from one place to another. So these wagons are moved through the rails, which are already fixed there. But when you move these wagons through the rails with the bricks, the problem is that when the rails are crossing, the bricks fell down. So it creates a lot of inconvenience for the workers when they have to move these wagons through these rails. So the problem actually originated from there, and then he thought, okay, how can I arrange this rails in such a way that it has minimum number of crossings? Then you don't have to worry about a lot of bricks falling out. So that was the original question asked in this field, and that's how this field has kind of developed.
And then what are some like current applications of graph theory?
For a graph theory, it has a lot of applications right now because if you look at the Google page rank, it is based on graph theoretical algorithms. The graph neural networks use the idea of graphs in it. And if you look at the Facebook friend suggestions, that also based on how the people are connected. So all the fields which you have some objects and the connections between the objects, there you can apply graph theory. So it has a wide variety of application nowadays. And even if you look at the chip in your mobile phone, the arrangement of elements in the chip can also be considered as one application of graph drawing. So I didn't say that it's currently used there, but this is what we looking forward. We can manage these the chips in the future, because the current research in graph drawings is in a very um, recent stage. What I said is it's not developed that much to take care of all the real world problems. We are only looking at the complete and complete bipartite graph nowadays. So this is a very two basic graphs we have right now. So we have to extend our idea to different type of graphs, then only we can really come forward to the real world. But we hope that in the coming years we could apply it more further. But if you just ask me about the graph theory, it already have a lot of applications nowadays. Also in the chemistry, if you look at the structure of a molecule, the bonds between the molecule, these all things have, for example, the Wiener index and kind of things have originated from graph theory, and there are people who are studying these things. So nowadays graph theory is very much globally applicable field.
And then I think you mentioned before that graph theory sometimes is like related to computer science, or like your area of research sort of has like the intersection between computers and graph theory. I was just wondering like how much of the math you do is like with a computer versus like by hand.
If I want to really know the results, so we have a database of a lot of graphs, different ways of drawing the graph. So if I really want to analyze some result, in this database, then I have to create a program that runs through all these graphs, because there are millions of graphs uh, which should be taken care of. So in that case, I couldn't do that by hand. So for that, I need a computer program to run through all the graph and check whether the result is correct or not. But once I know what happens in these graphs, but these graphs are not a generalization of graphs. Maybe it's a graph of 10 vertices or 5 vertices and so on. So I could analyze my hypothesis in graphs which have smaller number of vertices. But since I want a result in n number of vertices in a generalized setting, I can look at these results, and then it gives me an intuition of how it could work in a general graph. Then I can work on those intuition. In that moment, I need pen and paper, because I couldn't put 100 vertices into my program, because even with 10 vertices, it's more than 10 million graphs I have to deal with. So for initial observations, I use computer science or programming to obtain the results. And then I should think about it and use previous results or other existing theorems, or modify something to get a generalized result. So in that way, I'm combining both computer science and mathematics here. But on the other side, if you want to study about algorithms, you can also learn a lot of algorithms related to graph theory and so on. So in that way, also the theoretical computer science also use graph theory a lot, but that is not my area of research, because I'm from mathematics background, so I didn't went that far into the theoretical computer science. But there are applications, or there are people who are working in theoretical computer science and uses graph theory for their research for algorithms and complexity and things like that.
And then I think you mentioned that you work with graphs from like 10 vertices to 100 vertices, to like n vertices. I was just wondering if you could like roughly estimate what is like the average size of like graphs, and as well as like number of graphs you have to work with. Is it like really big and like a lot of them?
Yes, even with 7 or 10 vertices, there are different ways you can draw a graph. So if you take a complete graph with 10 vertices, you can draw it in a very different ways. So even if you consider all different drawings of a graph with 10 vertices, goes more than 10 million, I guess. Only with 10 vertices. I think it's way more than that, but I don't know how many zeros it has. So I assume it's 10 million or more. But if you look at 100 vertices, I don't think that I can count it.
And then I was just wondering, if you have to look at so many different graphs, how long does like a research project typically take for you?
So what we do is that we don't look at each individual drawing. Um, we look at what are possibilities that the one edge go wrong or one properties go wrong. So in that way, you can see some obstacle right away. Okay, if something drawn like this, it is definitely going to happen. So you can look at the localized space, and if you fix things in the local space, the entire drawing might get fixed. So you don't look at each and individual drawings. Instead, you look at the possibilities of obstructions, and you found a way to redraw in each of these possibilities. So in that case, you don't have to look each and every graph, but you need an intuition what all could be an obstacle. That is the part which takes most of the time, because sometimes you miss an obstacle, then your result is completely wrong. So you have to be careful that you have covered all the obstacles, and you find a method to overcome this particular obstacle. So that's how we usually do the research.
And then I think you talked about like sort of developing this intuition. I was just wondering, like, what are some good ways to sort of develop this intuition you're talking about?
Uh, so one way is what I mentioned before is look at the smaller graphs and see which all drawings fails. Then you will get an idea, okay, these things failed, but what could be the reason why these drawings failed? Then you get an idea, okay, because this edge came here or this vertex is positioned like this, that's the reason why you couldn't go further. Then you get an obstruction. Okay, this is an obstacle I have. And then when you try to prove it, you are proving in a logical steps. In between, you might also get, okay, what happens otherwise? So if you are saying if A happens, then B occurs, then if B happens, C occurs, then maybe you end up in a place where, okay, the C or C dash can happen. Then you have to split it again. Okay, what happens if C happens and what if C dash happens? So it's more like you are thinking in a logical sequence, and there it also opens several possibilities, and then you tackle each possibilities and see what happens. So it's more like you get an intuition from smaller objects, yes, but these smaller objects might sometimes couldn't show all the obstructions or obstacles you have. Then while going through a proof, you realize that, okay, how can I make sure that this step is true? Then you think, okay, what happens otherwise? Then this happens, and it goes in a progressive way. I'm not sure whether I was able to convey this idea clearly to you, but
And then sort of on the same note, do you have any pieces of advice, suggestions, or like resources or recommendations for students, especially like young girls in high school who are interested in pursuing math, graph theory, or like theoretical computer science?
okay. I don't have a very specific answer, but I think there are a lot of opportunities or scholarships, otherwise outreach programs available. And if you feel like some subject is good for you or you are interested in something, just go with that subject for some time to see whether it really fits you. Maybe sometimes you feel, okay, this subject is good for you, but you're going deeper into the subject, you realize that, oh, maybe it's not that good for me. So it always better to check for some time to see whether that subject fits you. For that, it is very helpful if you go for some workshops, summer internship programs, or summer schools that's also on particular topic. If you like graph theory, go for summer schools in graph theory. I have seen many summer school happening throughout the world. So you can go to different places and meet people who are working in the area, and you will get more idea about what the subject is. When you're initially learning a subject, you might not realize what exactly it is. Only if you go a bit further, you will see, okay, this is what the subject is. So if you have a confusion between two subjects, or if you're not sure which is your subject, try out every possibility and then fix a subject for you. And it is always possible to jump from one subject to another. So don't feel like, okay, I choose this subject, I'm stuck here. No, almost of all subjects are interrelated. If I want to jump to algebra, I can also jump from graph theory because there are algebraic graph theory, or in the other words, there are combinatorial commutative algebra, which combines algebra and graph theory. So there are these ways in which you can also move to a different subject if you wish so. So try to attend workshops, internships, or summer schools to get more idea about it. Yeah.
Okay, thank you so much for coming to this call. It was absolutely fantastic. Thank you.
Thank you so much.